Okay, so let's get right into it. We've seen robots do some pretty amazing things, right? They can master incredibly complex games. They can assemble car parts with insane precision. But there's this one area, one final frontier, that's been surprisingly tough for them, handling soft, squishy, deformable objects. Things like clothes, cables, even food. Well, today we're going to look at a breakthrough that might just be the key to teaching robots how to deal with the messy, unpredictable, soft-bodied world that we all live in.
I mean, it seems like such a simple question, doesn't it? Why is a task that's basically muscle memory for us, like folding laundry, so unbelievably hard for a state-of-the-art machine? Well, the answer, as it turns out, has less to do with the robot's hands and everything to do with where it goes to practice.
You see, robots learn new skills by practicing millions of times in simulations. But here's the catch. Just look at what's happening in that top row. With a typical or naive physics solver, the simulation is just, well, it's a mess. The virtual cloth stretches out like bubblegum, it slips right through the robot's grippers, and it's full of these bizarre physics-defying glitches. A robot could practice in this wonky world forever and learn absolutely nothing that would work in real life. And this right here is what researchers call the sim-to-real gap. It's this idea that what works perfectly in a simulation often just falls apart completely in the real world. And when you're dealing with soft objects, it's not really a gap, it's more like a chasm. The physics of how cloth bunches and drapes and folds are so complex that most simulators just can't get it right, leaving you with a digital world that's a poor imitation of our own. So today, we're going to break down a whole new approach to solving this. We'll start with the core challenge, talk about a new reality check for these simulations, dive into what's called the SIM1 pipeline, uncover its secret sauce, the deformation-stable solver, and then finally look at the incredible real-world results. So, the fundamental idea here isn't to just give up on simulations. Not at all. It's about rethinking them from the ground up. The problem isn't that simulations are inherently fake. The problem is that they aren't properly grounded in the real world they're supposed to be mimicking. And this quote from the research paper just says it all perfectly. The key isn't just to run more simulations, faster, or on a bigger computer. The very first principle, the most important thing, is grounding. You have to make absolutely certain that the physics in your simulation actually match the physics of the real world. Only when you've done that does it make any sense to scale things up. This new way of thinking is called real to sim to real, or R2S2R. And instead of the old one-way street from a generic simulation to a real robot, it's a complete loop. You start with the real world, you build a faithful digital copy of it, you train the robot like crazy in that perfect copy, and only then do you bring that hard-earned skill back into reality. It forces the simulation to stay honest. So the system that actually puts this whole R2S2R idea into practice is called SIM1. Think of it as a step-by-step pipeline for creating a perfect digital twin of a real-world task. This diagram gives us the 30,000-foot view of the whole process. Over on the far left, in real scene digitization, SIM1 takes the real-world setup and scans it into the computer. That creates the sim scenario you see in the middle. Now here's the most important part. Using something called the deform-stable solver, the simulation's physics are painstakingly aligned with reality. Once that's locked in, the system can generate thousands of realistic training scenarios, which are then used to teach the final robot policy. So let's break down the SIM1 pipeline into its three crucial stages. First up is geometric alignment. I mean, you can't simulate folding a t-shirt if your virtual shirt is the wrong shape or size, right? So you start with a super accurate 3D scan of the real scene. Second, and this is the absolute heart of the whole thing, is dynamical alignment. This is about making sure the virtual cloth stretches, bends, and drapes exactly like real cloth does. And third, there's movement alignment, where you generate a huge variety of different robot motions to make sure the final skill is robust and can handle anything. And that brings us to the secret sauce. How in the world do you actually achieve that perfect dynamical alignment? This is where the real breakthrough is. It's a completely new kind of physics engine, something called the deformation-stable solver. The key difference is all about how these engines handle forces. So on the left, you see a typical solver. It's slow. When a robot pulls one corner of the cloth, that force has to travel through the virtual mesh point by point, almost like a wave. That delay is what causes all that crazy, unrealistic stretching. But the SIM1 solver on the right is fundamentally different. It uses what are called adaptive strain constraints. Basically, it sets hard rules about how much the material is allowed to stretch, and it enforces those rules instantly across the entire object. This diagram shows us exactly how this clever mechanic works. The system is constantly checking the distance between all the little connected points in the virtual cloth. And if any two points stretch too far apart, farther than they could in real life, bam! A virtual elastic constraint is instantly turned on between them. It's like a tiny, smart rubber band that only appears when it's needed to pull things back into a realistic position. This simple but powerful rule prevents the simulation from ever spiraling into that stretchy, glitchy mess. Now, the formal technical name for this technique is Augmented Vertex Block Descent, or AVBD, but you don't need to remember that. The key takeaway is that this isn't just some quick patch, it's a fundamental change to how the physics engine works. By adding these explicit rules, these smart rubber bands, about how much the cloth can stretch at every single moment, it makes the entire simulation stable enough for a robot to actually learn something useful from it. Okay, so having a stable solver is one thing, but you still need to tune it to match a specific real-world object. A cotton shirt behaves differently than a silk scarf, right? And that's where this calibration loop comes in. On the right, you have a human expert literally puppeteering a real robot. Its exact movements are streamed to the virtual simulator on the left. The expert then just watches both screens and tweaks the physics parameters in the simulation, things like friction and stiffness, until the virtual cloth behaves and drapes exactly like the real one. So after all this meticulous work, the 3D scanning, building a custom physics solver, the expert calibration, the big question remains, does it actually pay off? Well, it's time to put this new reality-grounded simulation to the ultimate test. And here is the payoff, clear as day. On that top row, you've got that buggy, stretchy mess we saw before from the naive solver, and on the bottom, that's the SIM1 simulation. It's stable, the folds are realistic, it drapes and moves the way you instinctively feel cloth should move. This is finally a virtual practice space where a robot can learn something that actually matters. And the results? They are honestly staggering. When they trained a policy only in the SIM1 simulation and then put it on a real robot, what's called a zero-shot transfer, it achieved a 90% success rate on the folding task. That means it worked almost perfectly on its very first try in the real world without any real-world practice. That's incredible. Not only did it work, but the data it generated was incredibly efficient. This is the data equivalence ratio. For every one real-world demonstration they performed, the SIM1 pipeline could generate 15 synthetic examples that provided the exact same training value. Think about the massive acceleration in data collection that gives you. And because they could so easily generate thousands of different examples in the simulation, different starting positions, slightly different robot motions, the final policy was way more robust. It showed a 50% gain in its ability to generalize and adapt to new situations compared to policies that were only trained on a small handful of real-world examples. So let's just look at this whole beautiful loop one last time. You start with a real-world scene. You use the SIM1 pipeline to create a perfectly physics-aligned digital twin. Then you can massively scale up the training data in that simulation. And the result is a direct, successful, zero-shot deployment on a physical robot. The sim-to-real gap for this task has effectively been bridged. And this leaves us with a truly exciting question to think about. This technology goes so far beyond laundry. If we can create these perfectly grounded digital twins for something as complex and chaotic as cloth, what other complex, real-world problems could we tackle next? Training surgical robots with unparalleled precision? Designing new materials with properties we've only dreamed of? Maybe even modeling complex biological systems? The ability to perfectly replicate and then scale reality in a simulation could be a fundamental new tool for solving some of our biggest challenges.